For most of humanity's history, the sun was one of the greatest mysteries of nature, and it's no surprise that many ancient cultures came up with numerous deities of some kind and worshipped this great light in the sky. After all, it's easy to see sunlight is hugely important to life on Earth, even if our ancestors didn't have the means to understand exactly how. Nowadays, we know the sun is a thing. It can't grant wishes or hear prayers, although there still are a few things that remain unanswered. Aside from ascribing divine powers to it, people have also observed the sun since prehistory. They were aware of its motion in the sky and the influence of the seasons. Anyone could see less sunlight during winter meant plants grew less, and there was just less food. Astronomy is by right one of the oldest sciences, and the ancient Babylonians were the first civilization we know of that applied a mathematical approach to describing what they observed in the sky. Only fractions of their work remain, mostly clay tablets, but from these we can gather they kept close track of the motion of the visible planets, stars and constellations, and the sun and moon, and were able to predict solar and lunar eclipses. Now, the ancient Babylonians did see eclipses as some sort of bad omen, but to be fair to them, they really didn't have any other means to really explain them. A fun fact about Babylonian math is that it's based around the number 60 sexagesimal, while our math is based on the number 10 decimal. But the number 60 base is to this day still in use. For instance, like in timekeeping, there's 60 seconds in an hour, and it's also still used for geographic coordinates and angles. Ancient Babylonian astronomers divided the 360-degree sky in 30 degrees and assigned 12 zodiac signs to the stars along the ecliptic, and we still use this system. Babylonian astronomy was adopted and developed further by the ancient Greek and spread to the Islamic world and all the way to India, and can be considered a first scientific revolution in the history of our species. The ancient Greek were the first to offer a scientific/philosophical explanation for the sun. The natural philosopher Anaxagoras lived from about 500 BC to 428 BC and was the first to come up with a correct explanation for eclipses. And in his time, he was both famous and notorious for his claims that the moon was Earth-like and that it had mountains and was inhabited and reflected sunlight rather than shining on its own. He believed that the Earth was flat and that it floated on strong air under it, and that disturbances in that air sometimes caused earthquakes. He's the first we know of to introduce the idea that life can exist throughout the universe. He also believed that the heavenly bodies were once torn from the Earth and were ignited by rapid rotation, and that the stars were fiery stones, and that the sun was a giant ball of blazing hot metal. Eratosthenes lived from 276 BC to 194 BC, and he's famous for his incredibly accurate calculation of the circumference of the Earth, with an error margin of less than 1%. He was also the first person we know of to try and estimate the distance between the Earth and the Sun. And in his writings we find the description as of stadia myriads 480,000, but the translation of this is ambiguous, implying either 4,080,000 stadia, which in modern values is about 750,000 kilometers, or 804 million stadia, in modern values about 150 million kilometers. The latter value is actually correct, but we unfortunately will never know what he actually meant. Aristarchus of Samos lived from about 310 BC to 230 BC and was the first person we know of to propose that the sun is at the center around which the planets orbit, and he arranged the then known planets in the correct order around the sun. He also attempted to estimate the distance to the sun and concluded it had to be between 18 to 20 times farther away than the moon from Earth. The correct distance is about 400 times the Earth-Moon distance. Just like Anaxagoras before him, Aristarchus believed that the stars were other bodies like the sun, just very far away from Earth, and he correctly assumed this because he could not observe any obvious movement of the seemingly fixed stars in the sky. This stellar parallax, the movement of the stars relative to each other as the Earth orbits the sun, is only observable with telescopes, so there was no way for him to prove his idea in his time. In the 1st century AD, the famous ancient Greek philosopher Ptolemy estimated the distance as 1,210 times the radius of the Earth, or about 7.7 million kilometers. Ptolemy's work remained one of the most copied and cited works of ancient Greek natural philosophy for centuries, mainly promoted by the Catholic Church, including the idea that the Earth is the center of the cosmos. Heliocentric ideas were generally dismissed, and this was not unique to Europe and Catholicism. Most astronomers around the world believed in a geocentric model of some variation for the fairly simple reason that that seemed to match observations the best, even if certain things could not be explained properly, and the model was often overly complicated. It was generally assumed that the sun was a kind of light or heavenly fire on its own, though there were different opinions on whether the moon and the planets shone on their own or simply reflected sunlight. Cultures around the globe kept detailed records of astronomical observations, and it were Chinese astronomers that observed sunspots for the first time during the Han Dynasty between 206 BC and 220 AD. The Islamic astronomers Ibn Rushd and Ibn Bara also made note of sunspots in the 12th century, though they suspected these were transits of the planets Mercury and Venus. In the year 1032, Ibn Sina concluded that Venus had to be closer to the Earth than the Sun, after observing a transit of the planet. Medieval Arab astronomers were known for their extremely keen observations and record-keeping, and especially the work of astronomer al-Battani had a major influence on the development of science and astronomy in the West. He was the first person to understand the nature of annular eclipses. When the moon is far away enough in its orbit around the Earth, its apparent size is too small to cover the sun completely, and so the eclipse appears like a very bright ring. The accuracy of al-Battani's astronomical data encouraged Nicolaus Copernicus to pursue his ideas about the heliocentric nature of the cosmos, and his work effectively became a revolution in science. Copernicus was born in what is now Poland, and he was a very busy man, active in the fields of astronomy, math, medicine, church law, economy, and local politics, and he knew several languages. He started to work on his heliocentric model of the cosmos probably as early as 1510, but he would not publish his book on the revolutions of the heavenly spheres until 1543, the year he died. And it may surprise you, but the book did initially not cause a lot of controversy, but it was considered entirely hypothetical, and Copernicus did make it overly technical and complicated in order to avoid controversy in the first place. Solar observations in the 17th century revealed more about the sun than ever, and this was mainly due to the invention of the telescope in the Netherlands, though who exactly invented it remains in dispute. English astronomer Thomas Harriot was the first to use a telescope to observe sunspots with in 1610. Galileo Galilei likely started to make his own observations of sunspots around the same time, but did not write anything down until 1612. Dutch medical student Johann Goldsmith and his father David used a camera obscura to get a better view of the solar disk. A camera obscura is a projection of an image from outside a dark room through a small hole in the wall, with the image becoming upside down and reversed. Another method of observing the sun was with a helioscope, which involved projecting the image of the sun on a white sheet of paper in a dark room using a telescope. This all made it much safer to observe the sun for obvious reasons, although Thomas Harriot made observations directly at sunrise and sunset. And there's no record of any damage to his eyesight, but I would still very much recommend against staring at the sun directly at any time of day. Galileo was the one that suspected sunspots were a surface feature of the sun and not exoplanets in Mercury's orbit, and the continued observation of sunspots by many people played a role in the new debate over the nature of the solar system. In Europe, Catholic doctrine said that the heavens were perfect and unchanging, an idea that goes way back to the ancient Greek philosopher Aristotle, but observations of the sun, the moon, and the planets provided evidence that this was untrue. Sunspot observations showed that the sun was rotating, and all this collecting of data would later help with determining the solar cycle. In 1663, Scottish mathematician James Gregory came up with the idea of using Venus and Mercury transits across the sun to calculate the distance between the Earth and the sun. Astronomer Edmund Halley refined this idea in 1677 after observing a transit of Mercury, which led him to realize that observations of the parallax of a planet, preferably Venus, could be used to determine the distances between the sun, Venus, and the Earth using trigonometry. Parallax is the apparent shift in position of an object depending on the point of view of the observer. Parallax is an effect that you can easily see for yourself how it works if you hold out your finger like this and close one eye, and then the other, and hold your finger perfectly still, and you will see it shifts in position even though you're not moving it. And so the idea was to carefully observe the transit of Venus from different places on Earth to try and calculate the distance to the Sun. And this was a scientific endeavor that took quite a while to complete, because the problem with transits of Venus is that they occur in a pattern that repeats itself every 243 years. With 2 transits 8 years apart, and then you have to wait either 121 years or 105 years for another pair of transits. And so it wasn't until 1769 that astronomers were able to calculate the average Sun-Earth distance as 150,838,800 kilometers, only 0.8% greater than the modern value. So I just wanted to tell this story because it proves that the people of the past were not dumb. They just had less means and less history behind them than we do, but they were very clever in their science anyway. In 1666, Isaac Newton used a prism to show that sunlight is made up of many colors. And this was another discovery that helped the scientific revolution of the time. Sunlight was not perfect, pure, and colorless, and this was a first step in understanding the true nature of light. Further research into the solar spectrum led to a new field of science in the early 1800s, spectroscopy. English chemist and physicist William Hyde Wollaston is famous for discovering the chemical elements palladium and rhodium, but his optical work was important as well, since he was the first person to notice mysterious dark lines in the solar spectrum. In 1814, German physicist and optician Joseph von Fraunhofer invented a special instrument to study these dark lines with, the spectroscope, a special kind of prism with which one could measure the position and wavelength of these lines. Fraunhofer observed over 500 lines with his spectroscope, and these are to this day called Fraunhofer lines. He also laid the groundwork for stellar spectroscopy by greatly refining the spectroscope, and he discovered that bright stars like Sirius also have spectral lines and that they are different from the Sun's lines. By halfway the 19th century, scientists were able to reproduce these lines in laboratories by filtering light through various kinds of gases. By doing this, they found that the lines are caused by each element absorbing a different and very narrow wavelength of light. This discovery led to spectroscopy becoming the best way to determine the chemical composition of faraway sources of light, like the Sun and other stars, atmospheres of planets and nebulae, without ever having to be anywhere near them. Spectroscopy remains one of the most important tools in the toolbox of astronomers. Now, back in the early 1800s, during early studies of the spectrum of the Sun's photosphere, some absorption lines were found that did not seem to correspond to any known element on Earth at that time. In 1868, English scientist Norman Lockyer proposed that these lines were caused by a new element he dubbed helium, after the Greek god of the sun, Helios. 25 years later, helium is isolated for the first time on Earth, found as a gas that escapes as a consequence of radioactive decay of heavy metals like uranium. Helium is a colorless, odorless, non-toxic, inert gas with extraordinary qualities. It does not seem to have a freezing point at normal air pressure and won't become liquid until it's at only 4 degrees above absolute zero. Just below that point, it becomes superfluid, a special type of liquid with zero viscosity. That means it will literally crawl up the edges of any container it's in. Considering we now know that helium is the second most abundant element in the universe, it seems a little bizarre it took such a long time to find out it exists. But to be fair, it is quite rare on Earth itself. Most helium probably formed from the Big Bang itself, but some still forms from radioactive decay of heavy elements. It's estimated that about 1/3 of all the material in the Milky Way is helium atoms, and this is quite amazing to consider. By the latter half of the 1800s, the source of the sun's energy puzzled many a scientist. Sure, it was clear that it emits heat and is some sort of energy source out there in space, but with what scientists knew at the time, they could not explain where the sun's energy output came from. Keep in mind, nuclear reactions like nuclear fusion were still decades away from being discovered. Some scientists suggested that the sun's energy came from chemical combustion, like burning wood or coal. However, calculations showed that such a process would only sustain the sun for a few thousand years, much too short to match the geological and astronomical evidence of the Earth's and sun's age, which back then was estimated to be a few million years at least. Lord Kelvin, one of the most prominent scientists of the time, suggested that the sun is a gradually cooling liquid body that's radiating internal heat. In 1854, Kelvin and German physicist Hermann von Helmholtz proposed the gravitational contraction hypothesis. Basically, what they thought was happening was that the sun's immense gravity caused it to slowly contract, and the loss of gravitational potential energy would be converted into heat and light. This hypothesis could explain energy production for tens of millions of years, and this aligned better with the age of the Earth as understood at the time. However, later geological evidence suggested that the Earth was much older, hundreds of millions, up to billions of years, and so this explanation fell short. The discovery of radioactivity and radioactive decay around the year 1900 allowed scientists to make accurate estimations of the age of the Earth for the first time, but that didn't quite explain where the energy of the sun came from. Some other scientists had proposed that maybe the sun might also be powered by meteors and other material falling into it, but this idea couldn't explain the sun's energy output for billions of years either. These hypotheses reflected the limits of the science of the 19th century, since the concepts of atomic structure and nuclear reactions wouldn't see the light of day until the 20th century. New Zealand physicist Ernest Rutherford is known for his pioneering research into atomic and nuclear physics. He developed a model of the atom with Niels Bohr and discovered the proton. In 1904, he also proposed the sun's energy may come from radioactive decay in its center. But it was Albert Einstein's famous mass-energy equivalent relation that provided an essential clue for the sun's energy problem. Though for a while, the gravitational contraction idea remained popular even if it couldn't fully explain everything. Still, the remaining questions kept haunting the scientific world. How do stars work? Where do they get their energy from? Why don't they collapse entirely in on themselves? It was British astrophysicist Arthur Eddington who played an important role in answering these questions in the 1920s. Scientists back then knew gravity caused gas and dust in space to collapse into stars, but they couldn't explain how stars didn't continue to contract and collapse in on themselves completely. Eddington proposed that radiation pressure generated inside the sun and other stars could counteract gravitational pressure and put stars in equilibrium. He correctly speculated this radiation pressure came from nuclear fusion of hydrogen atoms into helium atoms, in accordance with Einstein's E=mc² equation. This was quite remarkable given the fact that at this point in time fusion and thermonuclear energy, and the fact that the sun and other stars are composed mainly of hydrogen, had not yet been discovered. Many scientists at the time were deeply skeptical of Eddington's ideas, but the coming decades would prove him right. In her 1925 doctoral thesis, British-American astronomer Cecilia Payne demonstrated that stars were mostly made up of hydrogen and helium. The theoretical concept of fusion was developed in the 1930s by astrophysicists Subrahmanyan Chandrasekhar, Carl Friedrich von Weizsäcker, and Hans Bethe. Between 1937 and 1939, von Weizsäcker and Bethe worked out the details of how exactly hydrogen atoms could fuse into helium in the cores of stars. Bethe's 1939 paper, Energy Production Inside Stars, described the two main energy-producing nuclear reactions that powered the sun. Scientific progress had made that physicists were able to further theorize and test their ideas about how the sun works, and the discovery of nuclear fusion is by far one of the most remarkable in the entire history of our species. One can argue we've opened some kind of Pandora's box when we became able to artificially reproduce some of the nuclear processes that happen inside stars. During the Second World War, both the USA and Germany had physicists working on nuclear fission for military purposes. The only nation to ever use atomic bombs for warfare was the United States, when they dropped them on the Japanese cities Hiroshima and Nagasaki in 1945. Killing between 150,000 and 240,000 people, most of whom were civilians. In 1957, astrophysicists Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle showed that most of the elements in the universe have been synthesized by nuclear reactions inside stars, some like the sun. Coincidentally, 1957 was also the year the very first artificial satellite was launched into Earth orbit, and with this, scientists had a whole lot of new opportunities to study space from completely new perspectives. The first probes built to study the sun were the USS Pioneers 6, 7, 8, and 9, launched between 1959 and 1968. They orbited the Sun at a distance similar to Earth and made the first detailed measurements of the solar wind and the solar magnetic field. Since then, many more machines have been used to gather a ton of data on the Sun's activity and cycle, continuing the work of those ancient people that spend their time observing that great fire in the sky. They had all sorts of ideas about what the Sun could be, how it got there, and how it worked. And while it's easy to boast we have so much more knowledge at our fingertips, it is in part thanks to their efforts that we can even say that. And it's good to remember there are still quite a few things we still cannot fully explain about the Sun. Despite all our efforts, we seem to have only scratched the surface of solar physics. Some of the most significant puzzles are understanding the solar dynamo and predicting solar flares and coronal mass ejections, or CMEs, eruptions from the Sun's surface. We know the Sun follows an 11-year cycle of increasing and decreasing activity. The peak of the solar cycle is called solar maximum, and that's when there's the most sunspots, solar flares, and CMEs. At solar minimum, the Sun is mostly inactive for months or even years at a time. The 11-year cycle is fairly predictable and consistently falls close to this time span. We know this because we have data spanning back literal centuries, since the first time people started to observe sunspots with their telescopes and noticed they were coming and going. What we now have noticed is that the magnitude of solar maximum changes considerably from cycle to cycle. Some solar cycles have a peak over twice that of others. Generally speaking, we understand what drives the solar cycle. Because the Sun rotates at different speeds at different latitudes, its global magnetic field slowly winds up and becomes more concentrated, so to speak, producing more magnetic activity. Eventually, the magnetic field winds up so much that it disappears below the Sun's surface, and this is the basic solar minimum magnetic field. But the intricate physics that drive it from inside the Sun, the so-called solar dynamo, and why that causes these 11-year cycles with varying peaks remain poorly understood. Another key area of ongoing research is predicting solar flares and CMEs. Flares and CMEs send huge amount of charged particles into space at high speeds, and when these reach Earth, they can disrupt our electrical equipment, power grids, satellites, and all sorts of communication. If we know when one is coming our way, we can take measurements to mitigate the damage, but as it is, all we have are a bunch of machines keeping a close eye on the Sun. We will know very quickly when a flare or CME happens, but we don't know the mechanism behind these events. And so we can't make any predictions. We know there are way more flares and CMEs during solar maximum, but until we fully understand how the Sun works, there is not a lot we can do outside of keeping close tabs on our star. Every day, scientists are working to expand our knowledge and help us understand and predict solar activity. And every day, we take a few more steps towards truly knowing the Sun. The Sun is an enormous, naturally occurring thermonuclear reactor that converts 600 million tons of hydrogen into helium every second. So when our ancient ancestors figured it had to be some kind of otherworldly entity their feeble minds could never truly understand, they were not entirely wrong to believe that. Luckily for us today, the work of numerous scientists over the course of a few centuries has helped us to understand the phenomenon we call the Sun, our star, without which we wouldn't exist. It always amazes me how far we've come, but also how much there still is to discover. I have a couple more videos about the Sun and how it works and how the solar cycle can affect our technology here on Earth, so check those out if you want to. And if you don't want to, then don't, I guess. Thank you for watching. I hope you learned something new today, and I will see you in the next video.